Hello everyone, my name is Piyush Yerkuntwar. I am going to explain the topic of heat treatment, that is annealing. So basically annealing is defined as heating the steel to austenitizing temperature and giving soaking time. As per BIS standard, for 525 mm of sample, the soaking time will be 1 hour. So basically annealing is done to reduce the hardness and to relieve the stress for machining the material. For hypoelectroid steel, the austenitizing temperature is AC3 plus 50, and for hyperelectroid steel, the austenitizing temperature is AC1 plus 50. The types of annealing are: first, full annealing; second, box annealing; third, bright annealing; fourth, stress annealing; fifth, spheroidizing annealing; sixth, process annealing; seventh, isothermal annealing; and eighth, recrystallization annealing. In box annealing, the steel is heated to austenitizing temperature in a sealed container with carbonaceous materials, which minimizes the oxidization, giving soaking time as per BIS standard. For 525 mm of sample, the soaking time will be 1 hour, followed by furnace cooling. Annealing in a protective medium to prevent surface discoloration is called as bright annealing. Protective medium can be obtained by using use of an inert gas or by reducing typical gas atmosphere. A typical gas atmosphere consists of 15% H2, 10% CO, 5% CO2, 1.5% of CH4 and remaining N2.
Hi, I am Divyaratnauke. Today we are going to discuss normalizing. Normalizing is a heat treatment process that involves heating a metal to a specific temperature, holding it at that temperature for a period, and then cooling it in still air. This process helps relieve internal stresses, refine grain structure, and improve machinability. It is a heat treatment process used to achieve specific microstructural and mechanical properties in metals. The primary purpose of normalizing is to relieve internal stresses that may have developed during previous processing, such as casting, forging, or machining. The normalizing process involves heating, holding, and cooling. The metal is heated to a critical temperature and it is held at that temperature for a period, and then the metal is cooled in still air. Effects of normalizing. Normalizing can have several effects on the microstructure and mechanical properties of metals, including refined grain structure, reduced hardness, improved toughness, and enhanced machinability. Normalizing is commonly used in various industries, including steel production, aerospace, and automotive.
Good morning everyone. Today I am going to discuss the purpose of hardening steel. A critical technique used in industry ranging from automotive to construction and manufacturing. This process enhances the mechanical properties of steel, making it stronger, harder, and more durable. Steel involves Steel hardening involves heating the material to a specific temperature and holding it there for a certain period, then cooling it rapidly, usually through quenching. This process allows steel microstructure significantly improves its hardness and wear resistance. First is quenching process. Quenching is a vital step in hardening. After heating the steel to its hardening temperature, it is rapidly cooled using mediums such as water, oil, or air. Depends on the desired properties of the steel and grade. The choice of quenching medium is decided. Water provides the fastest cooling while oil is slower, reducing the risk of cracking straws. Hardening temperature and soaking time. The hardening temperature varies depending upon the carbon content and alloying element in steel. Typically it ranges from 800 degrees Celsius to 950 degrees Celsius. At this temperature, the steel enters the austenitic phase, where its crystal structure changes, allowing carbon to dissolve in a formally. Soaking time. How long the steel is held heat to temperature is called as soaking time. It ensures uniform heating and phase transformation throughout the material. Generally, soaking time depends upon thickness of the steel, but often calculated but as PI standard, for every 25 mm diameter, it is usually 1 mm. Microstructure of hardware. After quenching the microstructure of steel parameters the list of martensite. Martensite is a supersaturated solution of carbon and iron characterized by its middle structure. This phase is extremely hard but also brittle. To balance hardness and toughness, subsequent heat treatment process is called tempering is often performed. Properties after hardening. The properties of steel after hardening are significantly improved. Increased hardness. The martensite formation increases surface hardness, making the steel resistant to wear and abrasion. Second, enhanced strength. The steel can withstand higher loads without deformation. Third, brittleness. While hardening improves the brittleness of martensite, makes the steel more prone to cracking under impact. That is why tempering is often necessary. Conclusion. In summary, hardening is a transformative process that improves mechanical properties of heat to control heating, shifting, and quenching. The careful selection of hardening temperature, chopping time, quenching medium ensures the formation of martensite, delivering the desired balance between hardness and strength. Understanding this principle is essential for engineers and metallurgists to design components that must withstand demanding conditions. Thank you for listening Thank you for listening, and I hope you gained some valuable insight into this hardening process.
Hello everyone, my name is Hardik Mesham and today I am going to explain you a topic of heat treatment, that is tempering. Tempering is a process in which heating the hardened steel below lower critical temperature, holding it for some time and then slowly cooling. Tempering is always done after hardening process. Tempering is a final operation in heat treatment. Tempering is done to relieve internal stresses developed due to rapid cooling of steel during hardening process, to reduce hardness, increase ductility and toughness, to eliminate retained austenite. Tempering consists of 5 stages. In first stage, steel is heated from 80 degree to 150 degree, which cause formation of epsilon iron carbide, which reduce internal stresses and give hardness of 900 VPM. In second stage, steel is heated from 150 degree to 230 degree, which reduce internal stresses and decrease hardness up to 800 VPM. In third stage, steel is heated from 230 degree to 280 degree, due to which retained austenity is converted to martensite. In addition to this, there is a formation of a small globular cementite. The hardness may be reduced up to 500 VPM. In fourth stage, steel is heated from 450 degree to 650 degree and gives soaking time of 1 hour, which cause growth of carbide particle called a secondary sobit. It contributes to improved tool toughness. In fifth stage, steel is heated between 650 degree to 720 degree. There is formation of large globular cementite particle called spheroidity, and we get maximum ductility, minimum hardness, excellent machinability and soft job with hardness 500 VPM.